Thank you. Welcome to the participants. We will now play the recorded speech of Mr. Sampath. Mr. Sampath is a chartered accountant based in Chennai, connected with a lot of schools and colleges, and he takes a lot of interest in our activities. And that's how we have Mr. Sampath here. We'll have the recorded speech of Mr. Sampath played now. Thank you. Over to you, Sadiq.
Good evening, students. I welcome students from various countries including India, United States of America, United Kingdom, and Dubai who are participating in this webinar. My special welcome to NASA scientist Mr. Jaideep Mukherjee, who is going to speak on James Webb Space Telescope. I would like to thank my good friend Mr. D.V. Venkatagiri for giving me the opportunity to meet all of you at today's meeting. Unveiling the Universe, how the James Webb Space Telescope JWST can help students. The James Webb Space Telescope represents a revolutionary leap in the space exploration and astronomy, offering students an incredible opportunity to dive deep into the mysteries of the cosmos. Launched in the month of December 2021, the JWST is the most powerful space telescope ever built, designed to observe the universe in unprecedented detail. It allows scientists and astronomers to look back over 13 billion years, exploring the birth of galaxies, the formation of stars, and even the potential for life on exoplanets. But what does this mean for students like you? The James Webb Space Telescope is not a tool for scientists. It's a bridge for students to explore the infinite possibilities of the universe. Let us unlock these possibilities together. Dr. Jaideep Mukherjee is a distinguished NASA scientist known for his contributions to space science and exploration. He serves as the director of NASA's Florida Space Grant Consortium, where he plays a key role in promoting space-related research, education, and outreach. Dr. Mukherjee has been instrumental in fostering collaborations between and academic institutions, helping to inspire and train the next generation of space scientists and engineers. His work encompasses a wide range of areas in space technology and is deeply committed to advancing space science education. With a career spanning over decades, Dr. Mukherjee has made significant contributions to NASA's missions and the broader aerospace community. With this, I welcome all of you once again. Thank you.
Our special thanks to Mr. Sampath Kumar, participants, especially to Mr. Jaideep sir. We are very hopeful that the new connection that we have established with Mr. Sampath will help us to take our mission forward to more and more number of students. Jaideep, as the students are beginning to log in, I will take a few minutes before I request you to start your presentation. Is that fine with you?
Yes.
Thank you, Jaideep. Greetings to all the participants. Explore the Space is delighted to have you all for this exciting webinar on James Webb Space Telescope by NASA scientist Jaideep Mukherjee sir. We welcome students and faculty members from various colleges and schools across India for this webinar. We are excited that we also have registrations from countries like USA, UK, and Dubai. Our special thanks to Mr. Sampath for the inaugural address that he just made. The purpose of this webinar is to expose the participants, the youth from different parts of the world, to the engineering marvel that is James Webb Space Telescope. Explore the Space is fortunate to be doing a series of programs with Dr. Jaideep Mukherjee. Our relationship with Dr. Jaideep sir started way back in 2018 with seminars in Bharathidasan University, Trichy and SRM University, Chennai. He is a senior scientist at NASA and director of NASA's Florida Space Grant Consortium. He has played a pivotal role in promoting education and research in Florida, coordinating student-led experiments and initiatives. Dr. Mukherjee is also involved in advancing NASA's educational programs and inspiring the next generation of space explorers. Now, participants, at Explore the Space, we have a very specific and important role wherein we link the students with the opportunities in the space technology and industry. Now, we quite well understand the importance of knowledge acquired and information gathered from programs like this that needs to be leveraged as career guidance and opportunities. Now, to ensure this, we offer memberships for school and college students in Explore the Space. I have a very short presentation. Sadi, can you help me? That runs for a few minutes. I would request your attention there. Through our various services, we essentially link students with opportunities in the global space industry. For school students, we offer STEM education programs, space competitions involving challenges and innovation, and also provide information. We provide information on scholarships. For college students, we offer guidance on internships, projects. We offer a lot of hand-holding and mentoring through our vast network for the startups and also for the budding entrepreneurs. Next. This is the membership card that we give to students across geographies. They could be in schools or they could be in colleges. This membership in Explore the Space helps both school students as well as college students to have a very good network with the space ecosystem. Next, please. For school students, the workshop and the course that we provide helps them to deal with critical thinking and problem solving skills. We offer them information on latest developments in space exploration and global education avenues for space technology. Now, participants, we very well understand that the requirement of school students are definitely different from the requirements of college students. Because once they get into college, they kind of they are very focused on what they want to pursue. They are either into physics, chemistry, or engineering, or mathematics, whatever it is. The college students are more specific in what they need because, to a great extent, their career have been kind of set or defined by the course that they have chosen. Next. So what we offer for the college students would be a good deal of information on space technology and its applications involving communications, navigation, forecasting, national security, disaster management, television, etc. We also provide a good deal of industry information. Explore the Space had the opportunity to be part of the recently concluded Bengaluru Space Expo, where we had the unique opportunity of meeting a good number of top leading as well as startup space companies, both from India as well as from other countries. We also offer guidance on interview skills because uh, we we find from our experience that many Indian students who have how do I put it? They definitely have the kind of knowledge, they definitely have the kind of skill, but then when it comes to presenting to, it could be their first interview. So all of us have gone through this. I mean, people of my age. So when we talk about somebody who is at the age of 21 or 22, when they are going to appear for the first interview, they would certainly need some handholding assistance on interview skills. So what we offer for college students includes guidance on on interview skills, information about space industry, space and allied industries. I would like to mention that we are now in October. In the month of November, the Indian Ceramic Society is having a huge conference in IIT Madras. We all know that ceramics play a very, very important role in building the platforms on which the rockets fly. Mr. Jaideep can throw more information about that. There are companies in Hosur. Hosur is an industry belt in the state of Tamil Nadu, where we have some leading companies that manufacture ceramics that go into uh, the making of spacecrafts. So what we are trying to convey is space industry is driven by multiple segments. Space industry is driven by multiple subjects. So that is the message that we convey to our students through our courses. This is a list of, this is a very illustrative list of some of the leading Indian companies. We all know that space industry has been privatized in India. There's a big difference when we say that ISRO has not been privatized. ISRO continues to be a leading, good, top class public sector organization. Space industry has been privatized. So we have a lot of private players coming into the space industry. In fact, as we move forward, there are at least 450 to 500 major vendors of ISRO who have been with ISRO for the last 2 to 3 decades. Now, after the opening up of the space industry, many of the Indian players are gearing up to play a much bigger role in the Indian space ecosystem. The next slide will have some of the startups, again, an illustrative list of Indian space startups. We have Skyroot Aerospace, Agnikul. Agnikul is based out of IIT Madras. Pixel is based out of Bengaluru. We have Bellatrix Aerospace. These are all, this is a list of very impressive Indian space startups. So the Indian space industry is going through a lot of positive transformation with a lot of new players coming in, and the future is going to be exciting. Next slide, please. So we invite the students from various colleges and students to join as a member of Explore the Space. By joining Explore the Space as a member, you will definitely have the advantage of being connected to opportunities in the space industry. Thank you for your patient attention. Jaideep, with this, my presentation comes to a close. We have 15 participants. We are definitely going to have more number of participants. But Jaideep, I would request that we start the presentation of Jaideep sir. Is that okay with you?
Yeah, I'll try and share my screen.
Yeah, we need to respect those who have logged in time. So now we request Jaideep sir to start his presentation. Jaideep sir's presentation will have two parts. After the first part, there'll be some question answers, and then Jaideep sir will do the second part. So, yeah, Jaideep, I'm able to see the screen. It's
Okay.
perfectly visible.
Okay, thank you. I hope you can hear the sound from the videos, because last time we had an issue. But it's not important if you don't hear them. So thank you for the invitation to talk to students. I'm going to make a presentation on the James Webb Space Telescope, just because this is a great example of an engineering project which is going to lead to extraordinary changes in our understanding of the universe. So I want to give you a background on why the James Webb Telescope was built, the different parts of the telescope. And in the second part, I'll talk about some of the observations made by the James Webb Telescope to understand the universe. So there'll be two parts. The first part is mostly the engineering thinking, and I can't see my screen. Thank you. So I'm going to start with a 2 or 3 minute like a video trailer of the James Webb Telescope, which gives you an idea on what this is all about. One second. Okay, hold on a second. I'm going to stop sharing.
Jaideep, I have a suggestion. If you can click more in your screen,
no, it's nothing to do with that. It is frozen up here. Hold on a second.
No, just to ensure that we don't have mischievous students have their way. There is a button called annotation.
Yes, annotation. Slide annotation. Disable annotation.
We would request you to disable annotation.
After screen
After screen share.
Okay, I had to kill the presentation. I don't know what happened. It's never happened before. So
no problem, Jaideep. If you can email it to us.
No, it's got nothing to do with you.
Okay.
I making presentations every day. I just hope no one is playing with it from.
No.
Let me start all over again. I apologize for this, but let's start all over again.
Yeah.
Okay.
Just give me a second. It's loading up. Okay, there it is. So let's see now. Okay, do you see it now?
Yes, Jaideep. I'm able to see your screen, Jaideep. It's very clear.
Okay, great. So let's. I'm going to skip the video just in case this causes a problem again. So I wanted to tell you why we are choosing this test telescope. It's not just someone came up with an idea and said, let's go and do it. It's based on some suggestions, some recommendation by top scientists across the world. So the way it's done is every 10 years there is something called as Astro Survey. And they talk with top scientists and to figure out which of the big questions that should be answered. So, but for the year decade 10 to 2020, they had decided that we need to figure out a way to understand the beginnings of a universe, how life formed, how stars formed. And to do that, the only way we can do that is to come up with a big telescope which can see in the infrared, and I'll talk about that, why in the infrared, and it has to be in space. That's the only way we can figure out what's going on with the universe, how it started, and so on. So again, as I said, it's based on some recommendations by scientists, and then NASA then takes this idea and then gets proposals from various organizations, and they then work with them to either build the observatory, to build the telescope, and so on. It's a very complicated process. So the three main questions which we want to answer, and this is actually any person who has some thirst for knowledge would like to know: where did we come from? How did we get here? And are we alone in the universe? So these are three questions which I know when I was growing up, I always wondered where we came from, and are we alone in the universe? So to do that, what we're doing is we're going to figure out what happened when the universe was created, and that was called the Big Bang. So from the Big Bang, the first galaxies were formed. The galaxies are nothing but a collection of billions of stars. So that's what the first galaxies were formed. You want to find out how did it form, when it formed, and then how did the galaxies evolve in time. So the universe right now is about 13.6 or 4 billion years old. In the beginning, there were smaller galaxies, but we know that these galaxies collided, combined, and they evolved over time. So how did that happen? And then how did the first stars form? Okay, so we want to understand star formation. We want to understand how planets form from stars, because we want to really figure out whether we are all alone in the universe. We need to understand how stars form planets, and then are these planets good enough that they can create life? So do they have the necessary conditions to create life? And when I say life, I talk about the life form as we know. Now, we're not talking about silicon-based life forms. We're talking about carbon-based life forms. So to answer all those questions, we figured out that we need a space telescope. We need a telescope which is not on the Earth, because if it's on the Earth, if you have clouds, it can block a lot of the radiation coming from the stars. And of course, clouds can block light. So it has to be above the clouds in space. It should be an infrared telescope. And I'll talk to you about infrared telescopes and infrared in a couple of minutes. But just take my word for it. We need something called an infrared telescope. And then we need a telescope with a very large aperture. Larger the aperture, larger the light gathering power, and fainter the objects we can see. And the best thing about astronomy is that the fainter we see means we're going back in time, because those objects, when they're very far away, are very faint. So if you're able to see faint objects, usually they are very far away from us, and we can then see what was happening at the time after the Big Bang. So these were the three different criteria that were needed for the new telescope. So I apologize if a lot of you know about all these things, but I'm not very sure about the background of the audience. Just briefly, one slide. Electromagnetic radiation. We know electromagnetic radiation because we get sunlight. Sunlight is a form of electromagnetic radiation, which is called visible. But even from the sun, you have other forms of radiation reaching us. We have ultraviolet, we have X-rays, infrared, microwave, and radio waves. So the sun is emitting a lot of this radiation, but it's mostly emitting in the visible. In the same way, there are other objects in a universe which will be emitting more ultraviolet or emitting more X-rays. It all depends on the temperature of the object. As you can see at the bottom screen, here the temperature scale. So if the temperature of an object is like millions of degrees centigrade, it will be emitting mostly in the X-rays and gamma rays. If it is about 6,000 Kelvin, it will be mostly emitting the visible, like the sun. But if it is very, very cold, like dust clouds or newborn stars, they'll be emitting mostly in the infrared and the microwave. So those last electromagnetic radiation, different forms of radiation emitted by different objects in the universe. The problem is that some of this electromagnetic radiation cannot go through the Earth's atmosphere. Well, we know the visible light can go through the Earth's atmosphere. That's true, but if there are clouds, it blocks it. But technically, through the Earth's atmosphere, light can enter. Microwave radiation and infrared are mostly blocked. All the high energetic radiation like ultraviolet, X-ray, and gamma rays are blocked by the Earth's atmosphere. And we are so glad that it's blocked, because otherwise we will not be alive. But the problem is that if you want to study infrared radiation, if you are on the Earth, then a part of the infrared radiation is going to be blocked. And to avoid that, we want it to be above the clouds, above the Earth's atmosphere, so that we can capture the infrared radiation. So that's why we want to study in the infrared of two reasons. One is that if you want to look at new formed stars, then those stars are mostly, or new-born planets, they're mostly emitting in the infrared. And for that, we need to be above the Earth's atmosphere. So that's a very quick explanation on infrared. The other thing you want to understand is something called the Doppler effect, which I'm sure all of you know. But basically, the Doppler effect is, if you have an object, say emitting sound waves or emitting light waves like it does, this emitting these waves as you see. But if this object is moving towards you, and if you're over here to the right, if you look at the object, the waves are being squished together, okay? And away from you, away from the object, it's actually being pulled. It's being stretched. And you have noticed this when you are, say, on a train station and you're seeing a train approaching you. Venkatrakli, tell me if you hear this.
Jaydeep, I heard a faint noise. Yeah.
Oh, okay.
But
so as you hear that, you see how the pitch of the sound changes as the train is approaching you, and then as it goes away from you, the pitch changes again. Same thing happens with light. So if you have an object emitting certain amount of light, and if the object is moving away from you, then what happens is the light wave is stretched. And we say it is stretched towards red because red is a longer wavelength. A wavelength is nothing but the distance between two crests of a wave. So red light has a longer wavelength, blue light has a shorter wavelength. If the object is coming closer to you, the waves are squished, and we say it's blue shifted. It doesn't mean that the color changes to blue. Or for red shift, it doesn't mean the color changes to red. It's just an expression we use to say that the light waves are being stretched, and so it's being red shifted, or they're being squished, and this is why we call it blue shifted. So that is what happens when objects are in motion with respect to you. And from that, we can understand a number of things about the object, how far it is, how quick it is moving, and so on. But there's something else called the cosmological redshift. And why this is important, and that's why the infrared thing comes over here. See, our universe is not static. It is expanding. From the time it formed from the Big Bang, it's been expanding a lot. Space is expanding. Now, what happens is, when the universe was formed, it was very, very hot. And most of the radiation emitted then were like gamma rays or X-rays, very short wavelength. But look what happens as the universe expands, it stretches, it kind of stretches the radiation and moves it to longer wavelengths. So what is happening is, as the universe expands, the radiation that was emitted just after the formation of the universe, which is mostly gamma rays and X-rays, as the universe expands and cools down, it stretches the radiation, and then we see it now mostly as infrared because they have been stretched so much. So if you really want to find out the radiation that was emitted by objects right at the time of the formation of the universe, we have to look at the infrared, because we know that that radiation that was emitted right now has been stretched so much that it's in the infrared. And that's why we have to choose an infrared telescope, so that we can see the light or the radiation that is being emitted by the object billions of years ago. So here's what I was trying to say, light from the first galaxies have been redshifted, when I said redshifted, to longer wavelengths. So it started, say, as gamma rays when it was formed, or any object emitting radiation. And then as the universe expanded, it cooled down and is mostly now seen in the infrared. Maybe millions of years from now, if you look at these objects, they'll be mostly in the microwave and radio. But right now, the universe has expanded so much that we see mostly in the infrared. And here's most of the sun's energy is in visible light, right? And they're broken up into colors. But it's all visible light, and our eyes is a detector for visible light. But our eyes cannot detect infrared radiation. Our eyes cannot detect X-rays or gamma rays. For infrared radiation, you can take pictures of objects with an infrared camera, and that, for example, here on the left, here's a person holding a matchstick, and the matchstick is the hottest. That's why the color is whitish in color. The eyes are actually cooler than the face of the matchstick, so it's bluish in color. These are just colors given to the camera, given to the image, just to depict the difference in the temperature. But that's what an infrared image would look like if you take an infrared camera. Again, the one to the left, you'll see a cat, again, an infrared image of a cat. Here's an infrared image of footprints. Our body mostly emits in a temperature which is emitting infrared radiation. So it's very easy to, in the dark, in the night, the army uses infrared detectors because you can detect persons because they're emitting infrared radiation. Here are some more examples of visible versus infrared. So here's a visible image of meerkats, and here's the infrared image. Here's a visible image of a crocodile, and here's an infrared image. So very different. So that's what I want to give a quick background on infrared radiation and the redshift, because that's important on us understanding why we chose the telescope. So let's quickly go to the telescope itself. It's a very large infrared telescope. It has a very large primary mirror. I'll explain to you more about these parts. So the primary mirror is about 6.5 meters. As I said, the bigger the mirror, the more light gathering power. This actually depends on the area more than the diameter. So we figured out that if we want to detect the radiation being emitted by those objects just after the formation of the universe, we need to have a telescope which is at least 6.5 meters in diameter, so that it can capture the radiation of this far away objects. That's why you have to choose a 6.5 meter telescope. It's a successor to the Hubble Space Telescope. The Hubble Space Telescope is also orbiting the Earth, but it mostly observes in the visible and part of the infrared, while the James Webb Telescope is going to be mostly in the infrared. It's an international collaboration in the US, Europe, and the Canadian Space Agency. It's led by a Nobel laureate, a physicist called John Mather. The total cost is about $8.7 billion, so it's very expensive. But remember, it's this cost that we show you out here is a cost for everything, for labor, for parts, for fuel, for everyone who's maybe a janitor in a NASA center or an engineer. We take account all the costs, and it's about $8.7 billion over a period of about 10 to 12 years. It was launched on December 25, 2021 from an European rocket called Ariane 5, and was launched on French Guiana, which is near the West Indies. And later on I'll tell you why we chose that location to launch. Here's a replica of the James Webb Telescope. It's pretty big. This white thing that you see out is something called the sun shield, and I'll elaborate on that. Just to give you an idea, this white sun shield is about the size of a tennis court. So you see how big this whole telescope is. And I'll tell you why we have all those parts of the telescope. Here are the international partners, European Space Agencies. They provided two instruments, the rocket and the launch. NASA is in charge of the mission and the observatory, and the Canadian Space Agency, they provided two of the four science instruments. And here is the launch site over here. So these are the different parts of the telescope. Unlike a telescope which you see on the Earth, which is usually a long tube with mirrors inside, there are more to it than an ordinary telescope. So you have what is called the primary mirror. The light comes and hits this mirror, reflects off a secondary mirror out here, goes through this gap over here, and there are instruments at the back which can either take images or measure data, measure the radiation. This is a sun shield, which is the most important part because infrared radiation can only detect radiation from objects which are very, very cold, very, very cold. And to get those temperatures, you have to block the sunlight from interfering with the instruments and the mirror. And that's why we have what is called the sun shield, which blocks almost all the sunlight and the heat reaching the mirror. So the mirror can only get the infrared radiation that is being emitted by those objects. Here's the size of the mirror. On the left is the Hubble mirror, the main mirror of the Hubble. As you see, it's a circle. But look at the James Webb Telescope primary mirror. It is almost the shape of a circle, but it is made up of a number of different segments. Because the problem is that if you want to create a big mirror, such a huge mirror, first of all, it's going to be very, very heavy and it's going to sag at the center. And the second of all is because it's so heavy, it's going to increase the cost of the launch. The heavier the payload, the more fuel you need. The more fuel you need, the more expensive it is. So they had to make it into segments. And the reason they had to make it into segments is because if you want to fit this mirror in a rocket, if you put a whole mirror 6.5 meters, you need to have a rocket which is very big. Again, you have a big rocket, you need more fuel, more expensive. So they created this segmented mirrors because then you can fold it. You can fold this mirror to fit into the rocket, and then after it's launched, the mirror unfolds itself. And I'm going to show you animations for that. Again, why are these segments hexagonal in shape? Why aren't these mirrors not circular in shape or not oval? The problem is if you take a circular mirror and you try to fit all the circular mirrors, there'll be gaps. So instead of having hexagon out here, if you put a circle here and a circle here, there'll be a gap in between. And we can't allow that. So the best way not to have any gaps is to have this hexagon shape, which will not only allow the parts to fit together and to almost form a circle, but also will help us fold it along a couple of axes. So that's why the mirror is segmented and not one whole mirror. Again, as I said, the most important power is the light gathering power, not the diameter of the mirror, but the light gathering power. So it's the surface area. And we look at the James Webb Telescope, look at this light gathering power. It's huge. Area is huge compared to the Hubble Space Telescope and compared to Spitzer, which is another infrared telescope orbiting the Earth. Spitzer is very small, as you can see. Hubble telescope is small compared to the James Webb Telescope. So this light gathering power, which is the mirror area, is most important. As you can see, the James Webb Telescope is mostly the infrared. The Hubble Telescope, visible and partly infrared. Spitzer is again mostly infrared, but it's very small, so it cannot detect fainter objects. Again, the primary mirror has 18 hexagonal segments, 1.5 meters each. It is made of beryllium, which is why beryllium, because it's very lightweighted. You can't afford to have a metal which is very heavy. So we use beryllium, which is very lightweight. It is coated with gold, a thin layer of gold. And the reason you use gold is because gold is a very good reflector of infrared radiation, as opposed to any other metal. So that's why we have beryllium, because it's lightweighted, and also because, and it's gold because it reflects infrared radiation very well. These are for engineers who love to look at numbers, and I'm not an engineer, so I don't remember any of these, so I put it on the slide. But one of the reasons for using beryllium, which has a low coefficient of thermal expansion, so if it is heated up, it will not expand. High thermal conductivity, and a very high stiffness to mass ratio. So it's very stiff. Because when you go into space and you go with a rocket, there's a lot of vibration. You don't allow anything to happen to the mirror. So that's why they chose beryllium for the mirrors. And of course, when you have these 18 segments, they all have to be aligned so that there's actually one smooth mirror. And what happens is behind each of these mirrors, there are actually, I think, about 5 actuators, which are small motors. And what these actuators do, they can move the position of each of these segments so that they become one smooth mirror. And to give you an idea that these actuators can move a segment by less than 10,000th of the diameter of a human hair. Think about that. It can make small adjustments, which is almost 1/10,000th of the diameter of a human hair. A very minute adjustment. I mean, I'm so amazed at engineers that they can do this. And one of the things about this whole project is you have to come up with new techniques and new ideas to do things. And this was one of them. How we can move it at very minute increments so we can create one very smooth mirror. And I'll show you an animation afterwards. Again, here's different parts of the telescope. You have the sun shield, you have the primary mirror, secondary mirror, the spacecraft buses where you have all the instruments. Sorry, let me go back. To control the spacecraft itself. The instruments over here. This is the sun shield. Let me talk to you about the sun shield, because this is an incredible piece of technology that had to be developed to protect the mirror. So what it basically is basically 5 layers of membrane. The membrane that they used is something called Captain. It was made by DuPont in the 50s. Now, each of these 5 layers is coated with aluminum, because that can reflect light and reflect heat. But they used 5 layers instead of one big thick layer, is because if you use one big thick layer, heat can still conduct through. But what here it is, you have 5 different layers with kind of vacuum in between, so it can dissipate the heat. So the heat by sunlight and the heat and it goes to the first layer, but then the heat dissipates off and it goes to the second. Whatever is remaining heat is again dissipated off the sides and so on. Till when it comes to the 5th layer, there's almost very little heat reaching it. Again, I think this is an incredible piece of technology that the scientists created, engineers created to protect the telescope. To give you an idea, the hot side of the sun shield is about 85 degrees Celsius. But as the heat is blocked by these 5 layers and heat is dissipated off, by the time you go beyond and come to the other side, the temperature is minus 233 degrees Celsius. It's amazing. You go from 85 degrees Celsius to minus 230 just by using the sun shield. And the reason you need that low temperature is because the science instruments, because it's detecting infrared radiation from objects which are at that temperature, If the temperature is not that cold, it cannot detect the infrared radiation. So you have to have a minimum of minus 233 degrees Celsius. Now, out of the 4 instruments, there's one instrument which needs a temperature lower than minus 233. And for that instrument, they have a separate, like a helium refrigerator called a cryocooler. And that refrigerator lowers the temperature a little more for that 4th instrument. But again, as I said, I'm amazed at this technology that we can go by just using sunshield. So here's what happens: the sunlight comes, some of the heat goes through, but here's because it's vacuum, less is conducted, and most of it is dissipated off from the side. As it goes from the 2nd to the 3rd layer, there's less heat, and there's less heat, and by the time you come to the 5th layer, there's almost no heat. Very little heat goes through the 5th layer to the instruments, and that's the key to the whole telescope. Here's again some examples of, here's the spacecraft bus, which has all the steering and control machinery. Here's the 5-layer sunshield. Here's the antenna to send data, receive data from the Earth, primary, secondary mirror. And here's the instrument module is out here, the science instruments which will get the images and the data from the observations. And that's the science module. Here it is. These are the 4 instruments. And this is just an animation which shows the location of the instrument module behind the mirror. So here are all the 4 different instruments, cameras and infrared. So what is called a spectrograph, what they take is to take the light, they break it up into different components, like you have the rainbow, and that's called a spectrum. And you can understand a lot about our stars and galaxies when you do that. So here, I'm not going to go through all the details, but here are the 4 different instruments: a near infrared camera, spectrograph, mid infrared instrument, and near infrared imager. These are the 4 instruments that we use. Of course, everything has to be tested. Testing. Without that, things don't work. So it was tested. The testing was done at the Goddard Space Flight Center. NASA has 10 centers. Kennedy Space Center in Florida, just across 10 miles from where I am giving this presentation, is where you have the launches. But Goddard Space Flight Center is near Washington, D.C., and they do a lot of astrophysics and so on. So a lot of the testing was down there. They there's what is called a shaker table. They shake it so much that it mimics the vibration you will feel when you have a rocket being launched. And you have to test it so that during a rocket launch, things don't break. So they vibrate the table 5 to 100 times a second, and that mimics the vibration environment of a launch. Also, there's an acoustic test chamber, because when you have a launch, you have a lot of sound, and if you're not careful, the sound waves can actually cause problems. So there are ways to mitigate the sound. So they do a testing in the acoustic test chamber to see that the sound vibration don't cause problems. And there are also a lot more testing done, but that's a different talk altogether. Come to the launch. As I said, the launch was done from French Guiana. This is the Ariane rocket. Why French Guiana? Well, for 2 things. One thing is that as the Earth rotates, okay, when you launch a rocket, if you launch a rocket which is near the equator, the Earth rotates faster than if you have an object on the Earth's equator, and say you have an object, say near New Delhi or near Mumbai, the object at the equator is moving faster than the object higher up in latitudes. So if you have a rocket being launched at the equator, as the rocket launches, it also has the speed of the Earth's rotation to aid it. So you need less fuel. If you're launching a rocket in the opposite direction to the Earth's rotation, you have to counter the Earth's rotation, and you need more fuel for that. So you try to launch as close to the equator as possible. In the case of NASA, we go to the closest southernmost possible area, which is Florida. Uh, but the European Space Agency has a launch pad near French Guiana, which is almost on the equator. So it takes advantage of the Earth's rotation. And the other thing is, you want to have the rocket in a place that when it launches is over the ocean and not over land. Because if something happens in the rocket and it's over land, and if it breaks up, it'll cause problems with the population. So most of the launch pad, whether it's in India, whether it's in the US, elsewhere, are either on the coast or like in Russia, it's in the middle of nowhere, where if something happens, it won't cause any problems. That's why French Guiana was chosen, because the European Space Agency has a launch place near the West Indies. And here's the Ariane 5 rocket. And here again, if you want to know the different properties of the rocket, it's out here. It's very massive. It has 2 stages and so on. But as you can see, here's a diagram. You can see how the mirror has been folded so it can fit. If you had the whole mirror unfolded, then this whole top part of the rocket had to be bigger, so make it heavier. So this way, by folding it, they can fit inside the rocket. How much time do you have? Can you brief for the first part?
Jaydeep, we have another 5 minutes.
Okay, so I'm going to skip this because this takes 5 minutes, but it's not so important. But what I wanted to show you was the orbit. And this orbit is very important because the James Webb Telescope is not orbiting the Earth really. It's actually orbiting the sun. I'll tell you what's happening over here. So if you look at the solar system, you have the sun and you have the planets. The Earth is about 150 million kilometers away from the sun. Now, the Hubble Space Telescope is actually orbiting the Earth itself. It's above the Earth's atmosphere, so it can clearly look at objects. The Webb telescope is not actually orbiting the Earth. It's actually at a point called the Lagrangian point. I'll explain it in the next couple of slides. But it's 1.5 million kilometers away from the Earth. And what happens is, as the moon and the Earth goes around the sun, the Webb telescope, which is at this L2 point, I'll tell you what that is in a second, is actually going along with the Earth around the sun. So the James Webb telescope is always behind the Earth and the moon and the sun as it goes around, because you don't want sunlight to hit the telescope directly. So the Earth and the moon protects it. But why this point? Why this L2 point? So let me explain to that very quickly. This is actually one whole lecture in celestial mechanics. But there are, if you have 2 bodies, actually 3 bodies, if you have the sun and the Earth and say a small spacecraft, then these points L1, L2, L3, and these are points where the gravitational force, say you talk of the sun and the Earth, and talking of the spacecraft, then the gravitational force of the Earth and the sun and the orbital motion of the spacecraft, they balance each other. So what do I mean by that? Look at this L1 point, which is the point between the sun and the Earth. If I place an object out here, if I place a spacecraft out here, as an object, the sun is the most massive object, right? So it has more gravity, it exerts more gravitational force. So if I have an object closer to the sun, then that object will move faster compared to an object further away. So if you have an object between the Earth and the sun, this object is going to move faster than the Earth. But what happens is, if it's in this position, then the gravity of the Earth is also actually going to pull on this spacecraft. So the spacecraft is, if the Earth was not here, the spacecraft will be going at a very high speed. But as the Earth is out here, its gravitational force will kind of pull on this spacecraft. So the spacecraft will be actually moving at the same speed as the Earth. So at this point, the gravitational force of the Earth and the Sun balance each other. So any object out here is going to orbit the Sun at the same speed as the Earth. The same thing if we put an object at L2, which is behind the Earth. If it is because it's further away from the Earth, it's going to move slower, but the Earth's gravity will increase its speed. So in effect, if you have an object here at L2, it'll go at the same speed as the Earth as it goes around the Sun. And the reason James Webb Telescope is at L2 and not at L1, because if it is at L1, the Sun will hit it directly and none of the instruments will work. So that's why it's an L2. Why not L4 and L5? The same reason, you don't have the Earth and the Sun blocking. L4 and L5 are more stable positions compared to L1 and L2. So when the James Webb Telescope is actually at the point L2, it's not stationary at that point, it's actually making a small orbit around that point, a very small orbit. And as the Earth goes around the Sun, this James Webb Telescope is also moving around along with the Earth, but at the same time is having the small orbit on this L2 point, because if we don't do that, then it's going to drift away. If we just leave it at L2, after some time it just drift away, and we can't have that. We have to have that place star in that position. So the same thing as I said, the Webb is orbiting about 1.5 million miles away, what is called the Lagrangian point, and the Webb telescope is making an orbit around the Lagrangian point. The size of the orbit is the size of the moon's orbit around the Earth. That's what this is. So that's what the orbit is, and that's why it's so far away from the Earth, so that it can detect infrared radiation. And how do we talk to the Webb? Well, we're not talking about huge computers on the Webb, right? And not like what we use on the Earth, but you can downlink about 57 gigabytes of data each day with a maximum data rate of 28 megabits per second. Now, if you use 28 megabits, you would scream because you won't be able to watch anything. If you want to watch videos on your phone or on the internet, you need high data rate. But for the data that we need to get, and given the size of the computers and everything, this is what we have. We can download 57 gigabytes every day. And it takes about 5 seconds for the data to travel from the spacecraft to the Earth. It's traveling at the speed of light. It's just radio waves. But how do we communicate with the spacecraft from the Earth? So NASA has 3 antennas around the Earth. At any given time, one of these antennas can always get data from a spacecraft. So, for example, right now we have the Solar Radio Probe that can be seen by the Deep Space Network antenna in Australia. The one in Goldstone can see the Mars Odyssey and so on. It all depends. But NASA has 3 of them, and one of the 3 is always in touch with the spacecraft. And here it is, the ground control station at the I think it's the Space Telescope Institute in Baltimore, very close to Washington. So that's how we get all the data from the James Webb Telescope. So this is the telescope. As I said, I'm trying to talk about so many things in about 30 minutes. It's not possible. So I'm trying to give you an overview of the James Webb Telescope. So we'll take a break here for about 5 to 10 minutes, and then I'll talk of the observations and the astronomy part and the astrophysics part. So how do you want to handle this now,
Jaideep, we have some questions. Is it okay with you if I ask those questions
Yes.
that Jaideep, we have question number 1 from Kavya, who is from Dhanalakshmi Srinivasan College of Engineering. And Kavya's question is how the James Webb Space Telescope is working. I think she's asking about what powers it. What is the power? How does it get the energy?
So basically, the initial speed you get is from the launch itself, right? You have to Why are launches so expensive? Because you have to overcome the gravity of the Earth if you want to go beyond to other parts of the solar system or beyond to the moon. So the main thing is the launch, the fuel that we carry to launch the spacecraft away from the Earth's gravitational field. But once it's in space, you don't need much power because you already have the speed and you don't have any objects trying to slow it down with this gravitational force. Now you can deliberately take spacecrafts closer to an object to use their gravitational field to increase the speed, like India did with the Chandrayaan with the spacecraft. What they did was it launched it with a small rocket, so it did not have the speed to escape the Earth's gravity, but it went into orbit around the moon. It used the moon's gravitational field gravity to increase the speed and then flung it away. In this case, we don't have to do that. We're just going beyond the moon, and the speed was enough to take it to the moon. Now, the spacecraft has small thrusters to orient itself a bit to move to make this orbit around L2. But basically, you don't need fuel to propel the spacecraft because it already have that energy during launch.
Jaideep, can I ask the next question, please?
Sure, please.
Jaideep, this is a question from Sai Nikita, who is from SSN College of Engineering. And Sai Nikita's question is, what is the farthest extent that JWST can see? How far can it see?
Okay, so I was going to show that in the second part of the talk, or the second part, the latter part. But here's the beauty: they have seen an object which is about a few, I would say about 1,000,000 years from the formation of the universe. So we have gone back about 13.1 billion years in time. You have seen an object where the light left it 13.1 and 13.15 billion years ago, and it has reached us. And it's also going to see fainter or more distant objects as time goes on because it's trying to take images and get data from these objects. So right now, we have seen at least, we call it 13.1 billion light years. So a light year is the distance traveled by light in a year. Light travels at a speed of 300,000 kilometers per second. Think about this. At that speed, if you're in a spacecraft, you can go around the Earth 7 times in 1 second. That's the speed of light. And at that speed, light would take 8 minutes to reach us from the sun. So as I said, light is taking 5 minutes radio waves to reach the James Webb telescope because it's so far away. Light from the nearest star takes about 4 years. The light from the nearest galaxy takes us about 2 million years. Light from the farthest galaxy, which the James Webb has seen is about 13.1 billion. Light left at 13.1 billion years ago. So that's the farthest. Now, I'm very bad at numbers, so I'm giving approximate numbers. It could be 13.12 or 13.13, but around that number.
Jaideep, I'll have one more question before I request you to start the second part. It's a very interesting question from Gauri Sriram, a school in Kalpakam, that's near the Atomic Power Station. That's the Kendriya Vidyalaya school. The question is, why is JWST called the next generation of space? What Gauri is trying to ask is, what is really the previous generation if we are going to call this as the next generation equipment?
Very simple. The previous generation is the Hubble Space Telescope. Look what the James Webb Telescope has done. It's about 4 or 5 times bigger than the Hubble Space Telescope. It's looking at the infrared, so we can look at objects very, very far away. A lot of new technology has been used, like I talked about the Captain, talked about beryllium, the location of the spacecraft. All these are what was not there with earlier telescopes like the Hubble. So that's why you call it a next generation, because it's doing things that the other telescopes have not done in the past.
Dilip, can I request you to start the next part of the presentation, please?
Okay. So, as I said, I talked about the telescope itself. Now let's try and see some of the first observations. So one of the first observations, and this might answer a bit of one of the questions asked about how far. Now, I want you to think about this. Take a grain of sand in your hand and put it at arm's length. Then that part, that grain of sand at arm's length, that is the size of the sky the James Webb telescope was pointing, and it took an image, and that's what you're seeing right now on your screen. A very small part of the sky, a very small part of the universe. Now, what you're seeing, these blobs that you're seeing are all galaxies. Each of these galaxies contain about 100 billion stars like the sun. Some of the stars are bigger than the sun, some are smaller than the sun. But look at this variety in just that picture itself. If you really look at it carefully, there are more than 1,000 galaxies. Light from most of these galaxies left about 4.6 billion years ago. So we're not going back, right back to the beginning of time, but about 4.6 billion years ago. This diffraction, these are actually the one where you see this diffraction, the spikes. These are actually stars in our galaxy. But all the others are galaxies far away. And you see some galaxies are bluer in color, some are redder in color. The blue galaxies have mostly stars in them. The orange galaxies, red galaxies, a lot of dust. Because they have a lot of dust, they are reddish in color. But if you notice very, very carefully, you'll see right here this kind of elongated arcs. You know what these are? These are actually images of a distant galaxy far away, about 1 billion years after the universe was formed. What is happening is this group of galaxies, this is a cluster of galaxies out here. They all go around each other. This cluster of galaxies' gravitational field acts as a magnifying lens. So what it is doing is that this what you're seeing is the image of a galaxy very far away, farther away than this cluster. The only reason we're seeing it is because the gravity of this cluster of galaxies is magnifying the image of that galaxy far away. This was first explained by Einstein. It's called gravitational lensing. So it's amazing that we can see these. Again, these are red in color because it's very far away. Light is stretched is mostly the infrared, and the James Webb Telescope and see it. But you're talking about objects about 1 billion years. So, other interesting thing, the Hubble Space Telescope had looked at the same part of the sky. It took it 11.3 days to take an exposure so that you can see all these faint objects. The James Webb Telescope is so powerful and it is such a big telescope that it only took it less than a day, 20 hours, to get a better image than the Hubble did with 11-day exposure time, which shows how amazing this James Webb Telescope is. So that was the first image that was released to the public. Remember one more thing. The way NASA works is that you can ask for telescope time. I know you have to go through a vetting process, and if you're given telescope time, you're given a time when you can observe what we want to observe, and then you're given 1 year to work on the data and release some information. After 1 year, the data is open to the public, to anyone. Anyone can download James Webb Telescope data. So you have 1 year to work on the data. After that, it becomes public. So that is the first one that we saw. The second, I'm showing you different objects. The second important thing was actually a planet that was found going around another star in our galaxy. But why this planet is because we found that this planet has a puffy atmosphere around it. Forget looking at planets around other stars. Now we're detecting planets with atmospheres. Now, this star, the planet that is going around this star is about 1,000 light years away, which means light left it 1,000 years ago. But that planet that we're looking at is about half the size of Jupiter, but it's bigger than the size of Jupiter. It's the mass is less than half of Jupiter, but its size is bigger. So it's a different class of planets that we see around this star. It's bigger and less massive. Now, usually bigger means more massive, but here you're talking about bigger than Jupiter but less massive. The temperature is about 1,000 degrees Fahrenheit. So forget about life being over there as we know. But what is it? And the reason is that why is it so hot? It's actually orbiting very close to the sun or to the star. So it's so close to the star, it's about 1/9 the distance of Mercury to our sun. So see how close it is to the star? That's why it's very, very hot. And it takes about 3 days, Earth days, to make one orbit around that star. But the interesting part was that it found this puffy atmosphere and it found traces of water in the atmosphere. So how do we know that there is a planet? Because the star is so bright and the planet is just reflecting the starlight. We cannot see the planet directly. Right now, we don't know the technology. But we know there is something going on because we study the light coming from the star. If the planet is not in front of the star, it's on to say to the left or to the right as it goes around. There will be steady starlight. But as this planet comes in front, it blocks a part of the light coming from the star and we see a dip. And then it goes away, then again you see the whole starlight. From that, one way to figure out planets on other stars is to study the light from the star to see whether there's a dip. And from that, we can figure out the size of the planet, if there's 1 or 2 planets and so on. And we also can, what we call, find the spectra. So let's talk about a spectra. Spectrum is something like, it's like the rainbow that we have from a star, from the sun. The light from the sun, as it goes to the Earth's atmosphere, the water droplets in the Earth's atmosphere act as a prism. And the light, as it goes through, breaks up into its component colors. The same thing, what we can do is we can take a light coming from a star or a planet. We allow the light to go through a prism, or if you call it a diffraction grating. It's like a prism. And that breaks it up into its component colors. So what we can do is we can figure out the spectrum of the planet. So there are molecules in that planet's atmosphere. It's emitting certain wavelengths of light, and we can figure that out by studying the spectra. I'm not going into more details because that's again is one lecture in an astronomy class. But just take my word for it. You can figure out the molecules in the atmosphere of a star or on a planet by allowing it to go through a prism, breaking it up into different components. And this is what we saw. So when there's a dip, it means that the molecule is absorbing some of the light coming from the planet or the star. Because it's absorbing some of the light from the planet, we see it as a dip over here. And this dip corresponds to water molecules. So this is the first time that we have detected kind of water molecules in the atmosphere of a planet around another star. But again, don't think too much of having life over there because it's very, very hot. And the next one is actually what is called a planetary nebula. It's actually a death of a star like the sun. And as the sun gets older and older, it gets bigger and bigger, and it's going to slowly start ejecting its outer layers. Again, whoever is doing this, if you don't mind, please, thank you.
Oh, I'm sorry about that, Jaydeep.
No, that's okay. You have no control over it, but it's very sad to see someone doing this. I don't see it when I talk to students from other parts of the world, so please don't do that. So this is what's called a planetary nebula. It's a remnant of a star which has come to its end of its life. On the left, we took its image taken by what is called the mid-infrared light. And if you look very carefully, here we see one star. This is the star which is emitting this blobs of gases, and we're seeing it in the infrared. But with a better camera on the Webb telescope, we see not as one star but two stars which are going around each other. Now, the faintest star is the older star, and that star is actually emitting these blobs of gases periodically, and that's what you see. So this blob of gas far away was emitted a long time ago, and the blobs closer to the star was emitted recently. But this is what is called a planetary nebula. And if you look over here, you'll see this picture over here. This is nothing but a galaxy far away, and that can be seen in this picture. Here is just a quick animation of what is called a planetary nebula. So a star, and a later part of its life, like the sun, is going to puff away its outer layers periodically, and what is left behind the core is a star the size of the Earth. It's called a white dwarf. So there is a white dwarf at the center of that nebula that has been emitting these puffs of gases. But it's not one star, there are two stars around it. And that's what this is. So this is a dying star. There are actually two stars. This is what called ionized gases because it's really hot out here. All the atoms in that gas, the electrons have been ejected out because it's so hot, and we call it ionized. These are dust clouds far away, and that's where they're reddish in color. But here's ionized gas, so it's very, very hot. So that's called the Southern Ring Nebulous in the Southern Hemisphere. This is interesting. It's got nothing to do with science so much as to do with art. Now, if you are blind and you cannot see this, there is a way to convert the amount of radiation that you're getting. We talk in terms of wavelength. So red light is a certain wavelength, blue light is a certain wavelength, and so on. You can convert it to sound, and this is what it will sound like. Watch this. Hear this. So as the light changes, the sound, you're converting it to sound. This is just, it's not that they are emitting sound, they're converting it to sound. So if you're blind, you might hear this variation in the sound, and that will give that person an idea of the variation of the gases in the objects. I thought this was so very interesting that you can take the data, translate to sound, so that others can, so that if you're blind, you can have an idea what's going on. Here's another good example of beautiful galaxies. These are a group of galaxies which are interacting with each other. It's called the Stephan's Quintet. There are 5 galaxies in this picture. But out of these 5 galaxies, this one is actually closer to us compared to the other 4. The other 4 actually are going around each other. But it looks like, they call it the quintet because there are 5 of them in this field of view. This was taken with the Hubble Space Telescope, and you can see the different galaxies. Here you see 2 galaxies which are merged together. Here you can see an arc, which is actually because one galaxy is going close to the other, is drawing. It's called a tidal tail. As you see, here's another tidal tail. It's again the gravity pulling some of the gases and stars away. Here's a Hubble picture of the same thing. So again, you have 2 galaxies which are really close to each other. They're merging. Here's another galaxy. Here's a galaxy which is closer to us. And these all 4 galaxies are actually going around each other. So this galaxy is about 40 million light years away from us. So light left that galaxy 40 million years ago, while these other 4 galaxies are about 290 million light years away. So they are further away from us. But in the sky, the 5 appear like the quintet of galaxies. Now, why this is interesting? Because with the James Webb Telescope, we can look at one of these galaxies out here and look at the center of that galaxy. And because we can take the light or the radiation and break it up into its spectral components, we can figure out the speed of the gases. So what we call the Doppler effect. And we found out that there are these ions, argon, neon, molecular hydrogen, which are going at a tremendous speed. And the only way you can explain the speed of this gas molecule ions is that there's a very massive object at the center, one that you really cannot see, but we know it's very, very massive, because if it was not so massive, the gases would not be going that fast. And that is a huge black hole, about 24 million times the mass of the sun. Is actively pulling matter around the black hole. We don't see the black hole, obviously. Light cannot escape a black hole. But it's pulling matter in, and as it pulls matter in, it emits energy. And the energy is equivalent to about 40 billion suns. Think about it. That's the energy being emitted by that black hole. And it's about 24 million times the mass of the sun. Here's a star-forming region called the Carina Nebula, and here's the Webb telescope taking a picture of the Carina. It's about 7,000 light years away from us, 7,300 light years away. And this was a picture taken of this out part of this. This is a huge cavity, and there are hot stars in here expanding there. But the Hubble and the James Webb telescope looked at this part, and this one over here shows you the Hubble image, and look at the James Webb telescope image. Look at the difference. The James Webb telescope is looking at it with better cameras in the infrared. The Hubble also looked at it in the infrared, but this is better. And you can see all these different features. Let me go to the next slide. So you see these mountain-like objects? These are gases, but you know how big these mountains are? 7 light years across. So light would take about 7 years. Light takes only 8 minutes to go reach us from the sun. We're talking about huge objects. Again, these are just gas pillars. And you can see this wisps of gas out here. These are actually, there are hot stars over here which you don't see. They're actually interacting with the gases, and they're making it very energetic, and they're ionizing it. The electrons are being stripped off. And that's what you're seeing. Are these wisps of gas which is being evaporated by the hot ultraviolet radiation from young stars, which are in the cavity but you don't see. This is a picture of Uranus. On the right is false color, on the left is kind of true color. But what they do is you take pictures with different filters, blue, green, yellow, red, and then you combine them. The reason Uranus is this color, like bluish green, is because it has a lot of methane in its atmosphere. And what methane does is, as sunlight falls onto the planet Uranus, is absorbing most of the red light. That's what methane does. And the blue light and the green light is being reflected back. Red light is not reflected back, it's absorbed by the methane gas. And that's why we see it in that color. On the right-hand side is a false color representation, which comes up, tells you the different types of temperatures along. So this is the pole. This is not the equator of Uranus. Uranus is the only object in a solar system where it's tilted by 90 degrees and is spinning on its side as it goes around the sun, as opposed to the Earth and other planets, which are kind of tilted a bit, but it's spinning this way as it goes around the sun. Uranus is this, so this is the pole of Uranus. And it takes, I think, 80 years to make one orbit around the sun. So about 40 years, one pole faces the Earth and the other pole is away. This is again false colors, just to tell you the differences in the temperature. All the outer planets, Jupiter, Saturn, Uranus, Neptune, have rings. We have seen the rings of Saturn, which you can see from the Earth. But for the other ones, you have to go very close. For Jupiter, Uranus, and Neptune, you have to go very close to the planet. But James Webb telescope is just beyond the moon. It was able to take an amazing picture, infrared picture of the rings of Uranus. The ones pictures we had before were taken by Voyager as it went close by the planet years and years ago. So this is an amazing picture of the rings. Here's again, as you see, it's like Saturn is edge on. This one is face on because it's tilted by about 80 degrees. And the reason why it's tilted is because we think years and years ago, as the planet was being formed, it was impacted by a huge object, and that impact tilted it on its side. So this is a computer simulation which shows that if you take two objects of a certain size, certain speed, and it hits each other, it can tilt it to its side. So we think that's what happened, why Uranus is spinning on its side. Another very interesting object in our solar system is Enceladus. It's one of the moons of Saturn. Why is it interesting? Is because we think there is a liquid ocean underneath the crust. And the reason we know this because we have seen geysers, water geysers, coming up from cracks in the surface. So this was taken by Cassini as it went close to close to the moon of Saturn, Enceladus. On the left is what James Webb telescope saw. So what you're seeing is this huge plume of water vapor, which is extending about 20 times the size of the moon itself. You don't see the moon over here in the picture. You're seeing just the infrared image of this plume of gas, but it's huge compared to the moon itself. So we think that there is water under this crust of Enceladus, and that's why we see these water vapors. So here's Saturn, here's on the rings of Saturn. As you know, the rings of Saturn just tilted a bit. And again, the rings are, this was taken by visible light. And this is what we see in the infrared. You see different features with the infrared than you would see with the visible light. And those are some of the moons of Saturn. Here's Enceladus. And these are the different rings of Saturn. They're made of ice particles, by the way. We found the most distant black hole about 470 million years after the Big Bang. So to answer one of the questions that was asked, the farthest that we have seen, it's about 470 million years after the Big Bang. It's a black hole about 9 million times more massive than the sun. But the galaxy itself is not very massive. This is a very interesting galaxy. Usually, if you have a black hole which is very massive, the galaxy itself is maybe 300, 400 times more massive than the black hole itself. But here, we're seeing a black hole which is only 9 million times more massive than the sun, but the galaxy itself is only about 10 times more massive than the black hole. And that's very interesting. We don't know exactly why you have a galaxy which is so less massive compared to the black hole itself. But that's the farthest we have seen. This is the Crab Nebula, so here's the James Webb telescope. Here's the James Webb picture. The previous is a Hubble picture. And the Crab Nebula is actually a star which exploded called a supernova. It happened about 6,500 years ago. And you're seeing the remnants of the supernova. And it's better seen in the infrared than in visible light. This one is the Horsehead Nebula, and I think I've seen pictures of it. If it works, I don't know. So hold on one second. Yeah, so here we go. So here's an animation, a kind of an animation which takes you to the Hubble, to the Horsehead Nebula. It is in the Orion constellation, which I think you can see in the skies now. You can see the three stars of the belt of Orion. And one of the belt of Orion, you have this cloud. It's just gas, dust and gas. But this is the shape of a horse. This is with the Hubble telescope. But with the infrared, with James Webb telescope, we can kind of peer through some of the gases And this is what you see with James Webb Telescope. This is just a place where stars are forming. These are just huge blobs of gas and dust. And because it's a lot of dust, you cannot, you see the stars inside. The James Webb Telescope looked at it better. And then it focused on the top part over here. And so here you go. Here, this is taken by another spacecraft in the visible infrared. This is by the Hubble in the infrared. And the James Webb Telescope looked at this part, and this is what it saw. You can see so many features now. So here you go. This is about 0.8 light years across. Now this is actually cold molecular hydrogen gas. And there's some stars over here, not this one. This is a star in a galaxy. But there are stars, young stars far away, and the radiation from that star is eroding some of the gases. So these are ionized gases. Cold molecular is ionized molecular gas. Again, you can see all these things. When I say see, this is the infrared image, but you can also get the data from the spectra and get some idea of how hot it is and so on. This is the Eagle Nebula. Some of you have seen this picture before. This was taken with the Hubble Space Telescope years and years ago, called the Pillars of Creation. These are huge objects. So again, these are pillars of gas, and basically what happens is this was actually a huge blob of gas, and again a hot stars close by eroded away the less dense gas, leaving behind the dense gases as pillars. And you have seen this if you go to a desert, you see these huge chunks of rocks, like pillars of rocks. And these are actually big chunks of rock, but over the years, rain and wind eroded away the softer parts of the rock, leaving behind the towers, the rock features. Same thing over here. You have this huge blob of gas, but the radiation from the stars, hot stars close by, in that area, in that nebula, eroded away the smaller, the less dense gas, leaving behind the denser gases. So here we go. Again, from the Hubble James Webb Telescope, you can see the top part of here, and you can see the small pillars. These are actually the size of a solar system. And at the tip of each of these pillars are new stars being formed. We don't see it, but we're seeing the pillars. So again, gases have been eroded away. So you see this small pillar. Again, when I say small, it's the size of a solar system. And at the tip of each of the pillar is a new star being formed. So here's the difference. This is Hubble, and this is James Webb Telescope. And you can see so many other features over here that you cannot see in the Hubble Space Telescope. So these are some of the discoveries of the James Webb Telescope. Right now, I took this about an hour and a half ago. So in about a few minutes, you can go to the website to see what Webb is observing. So now it's going to observe an object just for calibration. So as I said, I took this snapshot about an hour and a half ago. So right now it is looking at this object just for calibration. But you can go to this website and see what James Webb is observing. So, there are so many other observations that I didn't have the time to go through. But I wanted to give you a flavor, and I wanted to help both the science and the engineering students to understand the telescope itself and some of the sciences that we have been getting on the observed James Webb Telescope. And I know I spoke about many new objects and new things without going to the background, but I tried to give you the minimal background needed to understand what you're watching. So I'm going to stop over there, Venkatagiri, because I think that's kind of the end of my presentation. And if there are any more questions, I can answer.
Thank you, Jaydeep. As I discussed with you this morning over email, I have a request. Can the questions be sent to you by email? Or
Okay.
is it okay if we share your email ID with those students who ask for it. Is that okay with you?
That's fine. Yes, that's okay.
One specific question that we have from one university is it possible to talk to the team that is managing the James Webb Space Telescope? I see that they have a website which gives information on what JWST is doing this hour. Is it possible to interact with them? Does the team encourage that? Is it possible at all?
No, no. So not officially. You know, and there's not one team. It's made of hundreds and hundreds of people. So it depends what you want to. So if you want to understand something of the operation of the telescope, you talk to the lead engineer.
Okay.
And on a one-to-one basis, yeah, they might request, they might allow to make a presentation to a group. So it's not individual. There's no one place you can go and say, I want to talk to someone. If it is observing, there are hundreds of scientists who are observing using the James Webb Telescope. Some of them might be able to make a presentation or talk to you about what they are doing. But no, there's no one location or one person who can do. And the person who's in charge is so busy, that that'll be tough. I'm not saying it can't be done, but it can be done at a very high level. So if someone from ISRO is talking to someone at NASA, they might do that.
Jaideep, would you encourage a bunch of students, if they're interested, to do some kind of a research or a project report about the findings of JWST? Is that a good thing to pursue? If a bunch of students are going to pursue that as a research project for their engineering or science degree?
Yeah. So as I said, if you are trying to do your PhD or some kind of a research project, a lot of the science data is available online. You can download and you can do. So if it is just for your satisfaction that you want to do something, if you have the tools, if you have the software, you can download data and you can figure out more about the objects. Yes, it can be done. If you are working on the PhD project, talk to your advisor to see whether there's anything that they can download, or you can talk to the scientists in particular, because they're all presenting papers, right? The papers are published. You can always email the person in charge of that paper to see if they can provide you more information on they can give you the data. But as I said, most of the data is available to the public after 1 year. Yeah.
After 1 year, is it?
Yeah. So they give the person who's doing the observations 1 year to work on the project, to come up with some science, and then it's released to the public.
Now, Jaideep, not necessarily PhD, but this can also be pursued by engineering students. Am I right? Say the third year of our final year, electronics engineering student, or electrical or computer science, if they want to.
They can do, but they need to have a background in astronomy, right? So yeah, nothing is impossible. So yeah, if an engineering student is interested in doing the science, again, you download the data. Then again, you have to have someone to advise you, to mentor you to do that, because you will need to have the tools, the software, to analyze the data. But it can be done. I'm not saying it can't be done. It can be done. If it is just for your own satisfaction, then there's no issue at all. You just would need someone to just guide you along the way. But if it is for research, then you go through your advisor.
I understand.
Now, for the engineering part, the other things that they can do is find out, how the instruments were built. Because that's instrumentation is one of the big things. So when I say an engineering student can be very useful, because they can design the instruments. And in fact, for any science mission, a science mission is led by one question, a science question. In this case, how was the universe formed, new planets, how do we find new planets. But who is doing everything? The engineers. The
The
engineers
engineers.
doing the telescope, the engineers doing the instruments. And then once you get the data, the scientists take over and do so. If you're an engineering student, maybe you want to, and all these things about the James Webb Telescope, papers have been published. If you're interested, you can look at some of the papers, get in touch with the authors,
Sure.
and see whether you can work more on that instrument or something like that. Can be done. I never say that something cannot be done. There's
Thank you,
always a
Jaideep.
way.
That's
if
very
you believe.
encouraging. I'm going to write to you a few questions based on that. There are a few interests which I'm not in a position to discuss with you in public, but then I'm going to write to you, and based on your advice, we'll be more than happy to take the next steps. On that note, Jaideep, on behalf of Explore the Space and all the participants, we convey our sincere thanks to you. As I have said many times, your energy and motivation is a great inspiration for us. And thank you so much, Jaideep. And as always, we look forward to your trip to India. Welcome to India this winter. We look forward to that.
Okay. Thank you.
Thank you. Thank you, students. On that note, we close this webinar. Thanks so much to Jaideep. Thank you again, Jaideep.
Bye.